Today we are going to be doing related rates, and these are going to be the bonus problems. So this is just an extension from the previous related rates video. So for example 6, we have oil from an uncapped well in the ocean is radiating outward in the form of a circular film on the surface of the water. If the radius of the circle is increasing at the rate of 2 meters per minute, how fast is the area of the oil film growing when the radius is meter? Okay, so the first thing we want to do is we are going to draw a circle, and then we are going to call this R because we're looking for the radius. So what do we know? We know the area of a circle is equal to pi r squared. Secondly, what we're going to do is take the derivative of that. So we have d big A over dt equal to 2 pi r times dr over dt. Now we have dr dt equal to 2 because we know that the radius of the circle is increasing at a rate of 2 meters per minute. Now, for number 3, we know that r needs to equal 100, or is going to equal 100. So we're going to take our previous formula and get dA over dt equal 2 pi times 100 times 2, and that's just plugging in our variables that we know. Simplifying it, we get 400 pi, which is roughly about 1,256 meters squared per minute. 7. A particle moves on the hyperbola x squared minus 18y squared equals 9 in such a way its y-coordinate increases at a constant rate of 9 units per second. How fast is its x-coordinate changing when x equals 9? So the first thing that we want to do is write down the equation that we're already given. So x squared minus 18y squared equals 9. So this is the equation we're going to be using throughout. And so we want to know when x is equal to 9, what does y equal? So what we're going to do is just plug our x in. So 9 squared minus 18y squared equals 9. And then we get 81 minus 18y squared equals 9. And then by doing subtraction to the other side and then dividing by negative 18, we get y squared equals 4. So y is going to equal plus or minus 2. Next, what we want to do is take a derivative of our first equation, which is that. So what we would get is 2x times dx over dt minus 36y dy over dt equals 0. Now we can write the other things that we were given. So we know dy dt, which is going to be our y-coordinate increasing, is going to be equal to 9. And then again, we already know that x is equal to 9. So we shall take now this equation and use it for number 3. So we have 2 times x. So 2 times 9, since we were given our x, times dx over dt minus 36, and this is going to be a plus or minus 2 times 9, remember we were also given that, equals 0. So we get 18 times dx over dt minus 72 times 9 equals 0. We get 18 dx dt equals plus or minus 648. Then we get dx dt equals plus or minus 36 units per second. Example 8. If the radius of a sphere is increasing at the constant rate of 3 millimeters per second, how fast is the volume changing when the surface area 4 pi r squared is 10 square millimeters? So let's go ahead and write down. So volume of a sphere is going to be 4 over 3 pi r to the third. So we're going to take our equation and do dv over dt is equal to 4 pi r squared times dr dt. And then again, what are we given? We know that the rate, so dr over dt, is going to be equal to 3. And we also know that 4 pi r squared is equal to 10. So again, we're going to take this equation and we are going to plug it in. So dv over dt is equal to 10 times 3, which is just equal to 30 millimeters cubed per second. So this is example 9. So a boat is being pulled into a dock by a rope that passes through a ring on the bow of the boat. The dock is 8 feet higher than the bow ring. How fast is the boat approaching the dock when the length of the rope between the dock and the boat is 10 feet? If the rope is being pulled in at the rate of 3 feet per second. So the first thing we're going to want to do is draw a picture to get a visualization of this. So right here is going to be the dock, and then it's going down, and then we have the rope, which is attached to the front of the boat. Here's our little boat. Then it is on water. So this is going to be our Z. We know that the dock is 8 feet higher than the bow of the ring. So this is going to be 8 feet. And then we have X. Just to know what we're talking about. So X is going to equal the horizontal distance from the bow ring to the dock. And then Z is going to equal the length of rope between the dock and boat. Just so we can make sure we know what those variables are. Okay. Now, for step 1, so what do we have? We have a triangle, meaning that we can use the Pythagorean theorem. So z squared equals x squared plus y squared, but y is our 8, so we're going to plug in 8 squared. So we know that for z, when z equals 10, that's what we want to get for our x value, so we're able to plug it in later. So we can do 10 squared equals x squared plus 8 squared. This is going to be 100 equals s squared plus 64 minus 64 to both sides. We get x squared equals 36, and then x equals 6. So for number 2, we're going to take our derivative of the first equation. So we get 2z times dz dt is equal to 2x times dx dt. And then we can divide 2 from both sides, and we get z times dz over dt equals x times dx over dt. And then we know that our dz dt, which is the rope is being pulled in at a rate of 3 feet per second, is going to be -3 because it is coming in. So it's going to be decreasing. So we're now taking this equation and plugging in the numbers that we have. So we know that z is going to be 10. So 10 times our dz over dt, which is -3, is going to equal 6 times dx dt. So -30 equals 6 dx dt. We are going to then get that dx dt is equal to -5. So we know that the boat is approaching the dock at the rate of 5 feet per second. So this is example 10. So at a certain moment, a sample of gas obeying Boyle's law, PV equals constant, occupies volume V of 1,000 cubic inches at a pressure P of 10 pounds per square inch. If the gas is being compressed at the rate of 12 cubic inches per minute, find the rate at which the pressure is increasing at the instant when the volume is 600 cubic inches. So what do we know first? We know that PV equals a constant. 2, take the derivative. So remember, we're using the product rule for this. So we get P times the derivative of v plus v times the derivative of p, and that is going to equal 0. So we know that dv over dt equals negative 12. That's given to us because it's being compressed at a rate of 12 cubic inches per minute. And then we know that v is going to equal 1,000 and p is going to equal 10. So now for 3, we can take this equation and we can plug in the numbers that we have, which will give us negative 12 times 10 plus 1,000 dp dt. So negative 120 plus 1,000 dp dt is going to equal 0. And then we can just simplify this. So 1,000 dp dt equals 120. Now we're going to divide by 1,000 on both sides, and we get dp dt is equal to 0.12 pound per square inch per minute. Example 11. So a snowball is increasing in volume at the rate of 10 centimeters cubed per hour. How fast is the surface area growing at the moment when the radius of the snowball is 5 centimeters? So the first thing we want to do is have our surface area be A equal to 4 pi r squared. And then we also want to know that our volume is going to be 4 over 3 pi r cubed. So we have our dA over dt equal to 8 pi r times dr over dt. And then our dv over dt is going to be 4 pi r squared times dr over dt. And then we know that our dv over dt is going to equal 10. And so if it equals 10, we are able to plug it into our equation. So we can do 10 equals 4 pi r squared times dr dt. So what we can do is we can actually split this to be 1/2 r times 8 pi r times dr dt. And then we can take this, which we can substitute it, so we can get 1/2 r times dA over dt. And now this is the equation we are going to use for number 3. So we know that we have 10 equal to 1/2, and then for our r, we know that's going to be 5 when the radius of the snowball is 5, multiplied by dA over dt. And then if we simplify that, we get dA over dt is equal to 4 centimeters cubed per hour. And this is our last example for the video, example 12. So if the diagonal of a cube is increasing at a rate of 3 cubic inches per minute, how fast is the side of the cube increasing? So what we're going to do is kind of draw this out. So because it's a cube, it's going to look a little different because it's going to be essentially 3D. So you have a side, this is another side, and then you have a third side. And then we can just give let this be z. So if we're looking at it, what do we have? We have our diagonal, which is u squared. It's going to be equal, so it's a little bit like the Pythagorean theorem, but not exactly like it. So our u squared is going to be equal to one side squared plus the other side squared plus the third side squared. So that is going to be equal to 3s squared. If we square root both sides, we get u equals s square root 3. Now, if we take this and we get the derivative, we get du over dt equals the square root of 3 times ds dt. Now, last thing we're going to do is take this equation. We know our du dt is going to be equal to 3. That is how much our diagonal of the cube is increasing by. So now what we're going to do is get 3 equal to the square root of 3 times ds over dt. That gives us ds dt is equal to the square root of 3 inches per minute. And again, that is the last example of this video.